So in this example, we've got a specific reaction that we're going to look at, and you're told, and again this is exactly what we got on your PowerPoint in the lectures, we're told that this is a SN1 reaction. So if it's SN1, we need to remember that substitution nucleophilic unimolecular is only going to depend on the starting material for the first step. So we're told that if we were to take this molecule and we were to treat it with water in the presence of an acid, then we actually on first sight look like we end up with exactly the same molecule. It is the same molecule, but the stereochemistry is different. So here we had one isomer, the S isomer, whereas in this SN1 reaction, we're told that we end up with a racemic mixture, racemic meaning equal quantities of both enantiomer. So we've seen in the generic reaction mechanism what this entails. It entails for SN1 loss of the leaving group to give a planar carbocation. That planar carbocation is then attacked from either face by the nucleophile, and that's what leads to the racemic mixture. So specifically what's happening in this case? Well, we've got acid and we've got water. So the first thing that happens we have to identify in this substrate is where is our leaving group, because we know in the first step of the reaction we lose the leaving group. Now this here, this hydroxyl group, is the leaving group, but it's quite a poor leaving group. And what we find is in the presence of acid we can convert this into a better leaving group, because this high electron density, the lone pair on the OH, can actually react with the H+, which would then make it into a better leaving group. And so then the first step of the reaction for SN2, we're going to lose that to give us our carbocation. What we also get at this point, because we've broken that bond and that's joined with H+, we'd also be getting water. That's our leaving group. So let's just put LG as our abbreviation for leaving group. So that gives us in this first rate determining step, so RDS rate determining step, this here is our planar carbocation. So we're referring to this. This is then going to be attacked by a nucleophile. So in our in our reaction we've got water. We've also eliminated water as a leaving group, so there's plenty of water about. Let's draw this out to see why it's a nucleophile. We've got lone pairs of electrons. So lone pair is our nucleophile. Arrows go from high electron density to the low electron density. That will attack. Remember we said in our generic reaction mechanism when it attacks it can attack from above or below this planar carbocation. So that will attack above and below the plane. Of the carbocation. But let's just be clear, it's of the planar, so that's a flat carbocation. So when it attacks here, we're getting a racemic mixture at this point. So this here is going to be racemic. It's going to attack above and below, so that's why we haven't shown the stereochemistry here, because we've got equal amounts of the up and the down. So just to be clear about the mechanism, we formed a bond between here and here. So here's our new bond that we formed. All the rest is the same. So this side chain is the same as that one. That side chain the same as that one. H the same there. The water has lost its lone pair of electrons, so it's positively charged. And just by losing a proton from this, we can then form our product. So note at this stage here, this is when it is racemic because it can attack above and below the plane. So if it's racemic here and all we're doing is moving an H+ from here to give the product, it will still be racemic at that point. So that's quite a tricky example, but it shows you how this is actually used in reactions. We've gone through the generic mechanism before and we've now applied it to a specific case. So loss of the leaving group in the first step of the SN1 reaction, and then attack on that planar carbocation by the nucleophile to give the product.